Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN, sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature, to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna. Hello, everyone. Good morning, good afternoon, good evening from me as well. I am Guilherme Martinez Roura from the International Telecommunication Union, and I would like to welcome you all for joining today's AI for Good event on biologically inspired AI, a framework for designing adaptive robots, organized by the ITU. Today's session will explore the development of robust, adaptable robotic systems that integrate softness and rigidity for intelligent shape control and interaction. Drawing on embodied AI and biologically inspired methods, it will highlight automatic robot design and adaptation using evolutionary algorithms. This session is part of the AI and Robotics Discovery Series, which features expert talks on the state-of-the-art developments in autonomous robotic systems to solve some of the humanity's biggest challenges. We have a very distinguished speaker today, but as always, we are counting on you, the audience and the participants, to help create a very interactive session. As a reminder, the audience can leave questions on the AI for Good neural network chat room that will be answered during the Q&A section. So without further ado, I would like to introduce our distinguished speaker today. His name is Kyrre Glette, and he is the professor at the Department of Informatics, Robotics and Intelligent Systems Group, and the RITMO Centre for Interdisciplinary Studies in Rhythm, Team, and Motion, University of Oslo, Norway. Kyrre, the floor is all yours.
Thank you very much for the introduction, and thanks very much for inviting me to speak here today. And I will then just go straight on with a video showcasing a bit of our research that illustrates very much of the methods we're using here at University of Oslo. So you can see there is a robot crawling on the floor in the lab, and you can also see there are some robots being simulated on a computer screen.
Kyrre, so are you meant to be sharing your screen right now?
Yes. Did it disappear?
I can't see it.
Oh, thanks. Sorry.
That's okay.
Then I will try to fix that. Then I will restart the video.
Okay, thanks, Kyrre. We can see.
Can you see my screen now?
Yeah, we can. Yeah, thank you.
Okay. Yes. So here you see the robot crawling on the floor, and you will also see then soon a video of or a robot being simulated on a PC screen. So these are our robot designed with biologically inspired principles on how they are constructed, and we are using a process called evolutionary algorithms to test out many different solutions and to find innovative solutions. So here you can see that the simulator is testing a lot of different combinations of building blocks for the robots and try to assemble them and see if they can move. There's a lot of trial and error, and some solutions just don't work, so they don't get carried on to the next improved generations. I'll get into details about the algorithm shortly. We also did 3D printing of the robots that we found to be most promising from the simulation, and then wanted to test it in the real world. So here you can see a 3D printer in action, printing layer by layer the components that constitute the robots. There's a need for some post-processing of these parts before they can be assembled with motors to produce a working robot that we can test in the lab. Okay, so that was a little introduction to what I'll be talking about. More specifically, I'll give you a little bit of motivation why we're doing this kind of research. And I want to show to you like this framework, the overall design principles of doing this co-design of robot morphology, the shape of the robot and the control of the robot at the same time. I'll talk a bit about some of the algorithms that we use, such as evolutionary algorithms. And I will talk about using simulators versus testing things in the real world in our research. We'll also talk a little bit about the principles that we use that are inspired from biology to create more, efficient and robust robots. I'll also try to look into some perspectives on sustainability. So the motivation for doing this kind of research, it's looking ahead into the future. We are doing, say, fundamental research. We are developing algorithms and methods that could potentially be deployed in robots in the future. So it's currently not stable enough to be used in typical real robots that have to do something critical. But our thought is that we would like robots to be more robust than they are currently. So today's robots prefer to work in structured, well-known environments. But we see that there is a need for robots to operate, say, in remote locations, dangerous locations, in, say, disaster areas, for example. And maybe they could be used for like long-term autonomy tasks, such as maybe environmental monitoring. And in this case, it would be nice to have robots that are able to recover from damage or adapt to new situations, that the robots are energy efficient and using new principles for building robots. We can see in the research that there is a lot of interesting new principles for building robots. So such as modular robots that can reconfigure into new shapes depending on the need. We see soft robots that have very specific ways of actuating, can change their shape, and by that being both quite robust and have quite interesting modes of locomotion. You can see down here an example of a robot that was constructed by the use of a spray gun. So there was like a foam sprayed by a second robot to build the robot parts. So one can imagine this technology getting more advanced in the future, and robots would actually be able to work in a team and repair robots or build new parts or body parts that are needed for the robots, or maybe change the environment around them so that they can solve tasks more easily. But these robots are, say, quite unconventional in terms of how to engineer them and how to design control systems for them. So it's a much more difficult task to design the control and also how they should be shaped compared to like what we have at our disposal as engineering methods. And this is why we go to the bio-inspired scenario. So we use what we call evolutionary algorithms as a way to design the robots, both the shape of the robots and the control of the robots. And we also look to principles for controlling the robots and how to build these structures from biology. Here's a figure showing the main principle of this framework. You can see that to the left, we have an evolutionary algorithm which can feed solutions, like say it's a randomly created solution in the beginning for testing in a simulator or on a real robot. And depending on how this behaves then in the simulator or in the real world, we can send back some information to the algorithm about the behavior, the features of the robot, and also on how good it is at doing tasks that we specify they should do. And then this evolutionary algorithm iterates. It's like an iterative process. It can do thousands or even millions of iterations, continually trying to improve the solutions that it creates. And there's also room for learning while these robots are evaluated. So it proposes new robot shapes or morphologies. And they might be like unknown how to control them. So there might be also like this learning process, some algorithm that improves them. And all this part here, which I will come back to, is on how to design these robots from say a string of numbers to a robot blueprint. And in this process, we use bio-inspired methods. So we look at this co-design approach, where we want to design both the morphology and the control of the robot at the same time. So this is opposed to like the traditional approach where you design the robot shape first and then you do design of the control after that. So we want to go to this holistic approach and see how we can produce like a good combination of control and morphology and how this interacts with the environment. So we can then create specialized robots for different situations. We also look at how we can do modular architectures for control. So we go a bit opposing to this typical trending methods of learning robots to move today, like deep learning approaches, which are very large neural networks. So we want instead to focus a little bit on efficient, small modular control structures that could also be robust. So here's an illustration of the typical evolutionary algorithms, where it starts by just generating a lot of random solutions to a problem. So these are strings of numbers that are randomly generated. They will then be evaluated in a simulator, for example, and they will be measured on how well they're performing as to a given objective that we have specified. For example, on how fast they can move forward. In the beginning, as you could see in the video in the beginning, the movements are quite erratic and not producing very much movement. But some of them still, because this can be a population of hundreds or thousands of robots, so some of them will actually move a little bit forward and have some promising behavior. So those solutions will be kept for future generations, and they will be modified. There will be some small changes, and you can produce a new batch of robots that can be evaluated. And this goes in this iterative loop, and it will gradually be better and better. So in the end, you might have then a good solution that satisfies your specified performance measure. And then you can take those solutions and produce them. So that's the traditional evolutionary algorithm. There are some modifications. You can specify multiple objectives that the algorithm has to optimize for. And then it can expose also like trade-off solutions, because these objectives may be in conflict with each other. But overall, it has a focus on optimization. And then there is a new family of algorithms called quality diversity algorithms. And these have the specific feature that they also want to explore many different solutions. So the end result of these algorithms is not just the one good solution, but it's like many different solutions that are also good at your given objectives. So for example, here you can see that there is a whole, like say, this is a huge map of each pixel in this map is a solution to a problem. So in this case, the authors, this is another research group that did this, have looked for various types of soft robots. So they still wanted these robots to move forward, but they were looking for all sorts of different combinations of building blocks for these robots, so that you can see that they found lots of different solutions to the same problem of moving forward. This could be very useful to explore what are the design options in a problem. So it could be very useful for a human designer to get an illumination of this search space. But it could also be used in an online setting in field if there is a way to leverage a repertoire of different designs. Could be different controllers or maybe some reconfigurability, such that you could, for example, change the shape according to a new environment, a new terrain, for example. These algorithms do test a lot of different solutions. So for example, a typical evolutionary algorithm could maybe use, say, 100,000 tests of different robot designs. And a quality diversity algorithm needs to test even more, maybe, say, 1 million designs. So it takes a bit of time to complete these algorithms, but still it's feasible, say, within 24 hours for an evolutionary algorithm, or maybe a bit more for a quality diversity search. So I would like to talk a little bit about what different approaches the field has to evolving robots. And you can see that like there are people who do experiments only using simulations. So this becomes more like an artificial life form or a virtual creature that moves around. So these are never intended to be made as a real robot, but still they could be quite interesting in terms of studying how algorithms work and maybe studying how biology could work, or maybe a different type of life. And it's a way of analyzing and through synthesis. And then on the opposite side, there are robots that are like fully functional in hardware. For example, the ones that we showed in the first video, that can be produced. It's not always so practical to produce these robots. So like if you test a new solution, it might take some time to actually go through the 3D printing process, for example, to actually construct a new robot shape. So there are some examples at modular robots that can more quickly be reconfigured. Also, these soft robots that we saw in the previous slides can be built of various types of building blocks that have different properties, often called voxels. And these robots are usually studied in simulation, but it's possible to build some of them by various techniques, and maybe in the future it's possible to build even more. But currently it's not so practical to build these robots. And then a bit about how the simulation or the evolution is done. So there are some experiments where they do only simulation, and there is no intent to produce the robots. But still, you can see quite interesting results from this. And then maybe the most common approach is to do simulation. So you can test a lot of different combinations without any fear of breaking the robots or doing anything bad. And you can test a lot of different solutions on parallel computers. So it's a fast process. And then you can take those that are most interesting and produce those as real robots. Then you don't waste so much material and time. On the right side, there is the approach of doing only hardware evolution. So this is a bit more slow, but it could be quite interesting. And I'll get back to that a bit later. So first, to show some examples from this simulation approach, where we do most of the evolution in simulation and then go on to validate some solutions in the real world. So in a way, this is a quite practical approach. You can test out a lot of different simulation results before moving to the real world. Ideally, it would be a perfect way to produce a robot that could be used for some real tasks. However, we do have a challenge in that the simulation is not always, or usually not, describing the real world perfectly. And the evolutionary algorithms do exploit this to create solutions that are not always working very well on the real robots. There are some methods to address this, but it's usually a challenge that requires us to either do a lot more computations to be sure that the robots are more robust, or maybe do some learning on the real robots once they are produced. This is called the reality gap or the sim to real challenge. So I'll show some examples from our own research on this. So from the video in the beginning, same experiment. We used a multi-objective evolutionary algorithm so that we could evolve robots that were both fast and also try to evolve robots that are not so big or like not so heavy. This is a little bit conflicting because the big robots are usually the fastest ones. But using this, we could get a selection of robots that we wanted to test in the real world. So we chose robots that were quite different qualitatively in terms of morphology. You can see here how one of the robots performs in the real world. So in this case, the challenge was we had a certain arena where we could measure the movements of the robots. So the first things we had to do was to actually have the robot learn how to turn, because there is a new body shape and we didn't know exactly how to make it turn. But we needed it to turn so that it wouldn't walk off the arena and not be possible to measure it. So we ran a multi-objective evolutionary algorithm to make it turn while not being too much displaced. And then we wanted to check the real-world performance of the robot. And in this case, the red box here is how well the robot performed in the simulation. And the black box is how well the robot performed in the real world. So you can see that some robots were okay in the real world, not too big mismatch, but other morphologies were actually really bad in the real world. However, we could do some additional learning on the robots once they were produced so that the controller of the robot was adapted to the real world. So this mismatch was then corrected and the robot was fine-tuned to this new setting. This basically shows that we could regain some of the performance and get back close to what we had in the simulator. Okay, then I want to show another example, and this is using a quality diversity algorithm. So in this case, we had we wanted to explore the design of linkages. So this is this interesting mechanical mechanism that we can use by having like one rotational axis and translate that into a movement. So by having just rotation in this point, we can get a quite interesting trajectory of the end effector, like the foot tip of the robot. And quite many interesting robot designs have been made by this. So it's a very, very basic and simple actuation from a rotational, like from a motor, and you can have quite complex trajectories. So we wanted to explore how we can evolve lots of different types of trajectories in case they could be built in different ways, and one could explore designs so that they could work for different types of terrains and so on. So we wanted to see how this could help us as a design tool. And then we used this map elites algorithm, a quality diversity algorithm, and managed to then fill up like a map with different solutions to the problem, which we could then use to build robots to test it. So in this case, we explored different ways of characterizing the solutions. So for example, there were properties on the mechanisms, like how many bars it used, and also properties of the trajectories of the foot tip. So like how much it may raise the foot tip, for example, how long contact with the ground. And once we had done this exploration of different types of characteristics, we wanted to reduce the maps so that it would be more tractable for a human designer to explore these different solutions. And then we select some of these to be produced with Lego bricks. So in this case, we chose Lego bricks because it was a fairly simple way to prototype our designs without having to 3D print. And it's quite nice in a way, as long as it doesn't get too complex. So in this case, we tested some designs, and you can see that the results lead to quite different behaviors by changing the composition of the bars. So in this case, maybe it was not so much about like automatic adaptation, but as a design tool to explore what's the design space of these kinds of robots. Okay, now I would like to talk a bit about real-world evolution. So in this case, we want to see how we can benefit from doing evolution only on real-world robots. So in that makes it it makes the reality gap disappear in a way, because then there is no transfer from simulation to reality. On the other hand, though, it's quite time consuming because this requires us to test every solution in real time on a robot. For example, you can see here on the right some research from Cambridge where there's a robot arm that can pick up robot modular components that are either motors or fixed blocks and glue them together. And then they were tested in this arena on how well they moved forward. Of course, this approach has the advantage that it can exploit and use all of the rich interactions in the real world that a simulator may not capture. But it's really technically challenging, and we don't see so much of this research because of this technical hurdle and lots of wear and tear on the robot parts and such. But we have done some research in this area, and it's on this robotic platform that I'm showing you now in the video. So this is the dynamic robot for embodied testing. So it's not exactly typical Boston Dynamics robot, but it is built by only one PhD student, and it has this particular mechanism that lets its legs be reconfigured, so it can change the length of the legs both in the upper part of the leg and in the lower part of the leg. So this allows us to reconfigure the robot in a way that we can test different morphologies. This mechanism is too slow actually to be used actively in a locomotion pattern. But it can be used in between to reconfigure to test different morphologies for an evolutionary algorithm. Here you can see a close-up of this mechanism. So then we were running an evolutionary algorithm to see if we can see something interesting from this purely real-world evolution. So here you can see the robot is testing various control systems, various controllers, and also reconfiguring itself. It's not so easy to see it, but it does test various lengths of the legs. And what we did was to have two conditions. One condition where we gave it optimal voltage for the motors, and another condition where we reduced this available voltage. So then the robots, the motors would be less strong in practice. And what we could see is that up to a certain speed, the evolution managed to find similar performance both on speed and stability, even if the voltage was reduced. But at the same time, the morphologies and control that was evolved was different. So we could see how evolution found a way to adapt to the different power constraint setting. So this could be useful, for example, if there's a scenario where the battery runs low or it needs to save energy. We also did an experiment where we tested the robot on different surfaces, so different types of carpets. And also in this case, you can see some waveforms here, and when the waves are different, it means that the morphologies that were evolved were different on these different surfaces. Now I would like to talk a little bit about how to code for the different structures of the robots. So the most straightforward way of doing this is to have this sequence of numbers that represents a solution to the evolutionary algorithm, to have this as a quite direct mapping to how the robot is going to look. So it could be that one number for the evolutionary algorithm is directly the length of the leg of the robot. This is actually what we did in the previous experiment to change the length of the legs of the robot. And also in this research here, you could see that there's a certain robotic structure, and it has a quite direct relation to the numbers that are processed by the evolutionary algorithm. The other approach is to use an indirect encoding. So this is like a generative approach. So you, instead of directly coding the solution, you code a recipe for building the body of the robot and maybe also the controller of the robot. So this allows for more like repetitive patterns, more regularity, and more compact descriptions. So for example, here you can see some compact descriptions that lead to quite complex shapes. So then the evolutionary algorithm works on this compact graph, which again leads to these different blueprints for the robots. And as for control methods, there are many popular approaches in evolutionary robotics. The typical most used one is centralized controllers. So there is one neural network that controls the whole robot. So like different outputs of the neural network will control different motors. And there might be some sensory input to this large network. But then there are also decentralized approaches. And then that means that every single motor in the different joints, in the different modules, have their own control system. So their own small neural network, for example. One popular approach to this is this central pattern generator approach, which is inspired by neuronal circuits found in biology that generate waves that can be used to control the robot limbs. And in this case, there is like each joint is kind of oscillating and actuating itself, but there might be some coupling between the different modules, such as like coupling through the body indirectly, or it could be also some neuronal connections that can help, for example, to propagate phase between different parts of the robot. There's also some quite interesting research using embodied control elements, such that you can, for example, choose to have some body parts that are contracting and some parts that are stiff. And together, when you assemble this, you will see some interesting locomotion patterns. So here's an example from our own research, where we studied the difference between a direct encoding of the body and an indirect encoding of the body. So there was something called an L system, Lindenmayer system, that we used as a principle for coding the body. And I will not go into details on how that works, but you can see that a typical example of a body coded with a direct encoding gives a quite, say, irregular shape. It manages to find solutions that perform okay, and quite interesting solutions, but there is little regularity in this robotic shapes. Whereas if we use this generative encoding, you can see that we easily can get something like a snake that jumps around. So this is like a very compact way of describing repetitive shapes. However, only when we couple it with a good decentralized control approach, we can see that we get this nice transmission of signals between the body elements, and that led to quite interesting morphologies to appear also. So you can see that this may be quite resembling of, say, insect type of solutions found in nature. Here's another approach that we have studied recently. We were inspired by how efficiently centipedes are moving in nature. So this is a collaboration with researchers in Japan. And they have studied centipedes extensively, and it seems like there are some common principles that are at play, even if the bodies of these different types of centipedes are quite different. So we were inspired by this finding, and we wanted to see if it's possible to build a decentralized control system that can be used to control several morphologies. So I will not go too much into details about this, but this shows one segment of our virtual centipede, where there is one central pattern generator type of circuit that generates an oscillation to move the leg, and there is some contraction. And this is all governed by simple rules of feedback from sensors, proprioceptive sensors in the body and from the foot touching the ground. And what we could see then by exposing this design controller to various types of morphologies is that the result is like different behaviors in the locomotion, but this is the same controller without any tuning of parameters whatsoever when transferred between different morphologies. So it will help us have like a robust adaptation to morphological changes. So this is something we would like to use further in evolutionary research of morphology and control. So it would be very useful for us to have a control architecture that can very easily adapt to a new proposed morphology. Then we would not have to do so much learning in this process. We also want to test this out on a real robot as much as we can, but we have not come that far yet. There's also quite a bit of research going on in doing lifetime learning on the controller of a robot once the new morphology is proposed. This is something we have just started looking into, so I don't have so much to report on that, but there's typically you want to do a search or an algorithm learning process that is more efficient, but because this is something you do for every new robot you test. So if you test 1 million different robot designs, you would have to do this learning 1 million times. So it shouldn't be too slow. And that's why we usually try to do some data efficient algorithm to do learning. It could be something like reinforcement learning or Bayesian optimization or other more like local search algorithms. This is in contrast to the evolutionary algorithm that explores new morphologies. This can be a more exploratory algorithm like what I have described so far. Okay, so I would like also to highlight that in terms of like sharing our knowledge about this, we are quite interested in proposing that others can make use of these frameworks to do their own experiments. So we have made several platforms that people can download and try. So we have one for the 2D environment, and we have one for a 3D environment. And these are both using this gymnasium structure, which are easy to plug into and compatible with many reinforcement learning approaches. And then we have open sourced and also open hardware description of the dynamic robot for embodied testing. Of course, it's a bit complicated to build this robot, but in theory, it's possible, and you can download all the design files from us. The most recent framework we have been working on is this evolving modular robots framework, which is building on the Unity game engine. So this is possible to download for free, and one can plug into evolutionary algorithms or other types of algorithms to test automatic robot design. So it leverages a system called Unity ML agents, and through this we can plug the evolutionary algorithm, and one can easily design new modules and types of building blocks structures that can be used for exploring evolutionary design. As for the environmental impact and this kind of sustainability perspectives, I think that our algorithms are, in a way, they're doing a lot of computation when it comes to testing new solutions. You could have, like, say, 1 million tests for different solutions in this quality diversity approach, like the map elites. And in the basic evolutionary algorithms, maybe not so much, but it could still be hundreds of thousands. Usually, though, there is not so much like training of machine learning models that are very big and complex. So I think still these are things that can be done in a, like, say, 24 hours on a powerful workstation, or maybe by distributing on a couple of workstations and maybe let them run for a couple of days. So there's some power consumption by these algorithms, but it's not colossal, I would say. And of course, if you want to test a lot of new 3D designs, you need to print them, and there's some plastic going into this. I think it would be, if one wants to do really large scale testing of real world robots, it would be nice to use some kind of recyclable material in this process. But there is a hope in this process that we can actually be more efficient by using what nature has already found for us as efficient designs, energy-saving designs, which has been found by the process of natural evolution. So this is a process that has gone on for a long time, and there's been put a lot of energy from the sun into this process, and there are surely some solutions here that are very relevant for us to use, so we don't need to reinvent everything every time we make new robot designs. And I also think that there's a potential that the resulting designs from these algorithms can be quite energy efficient and material efficient. So, for example, optimizing for use of less material is one possible way to steer these algorithms. So one known example is this Japanese bullet train, where the nose of the train was optimized by an evolutionary algorithm to have less aerodynamic resistance. It's not maybe exactly a robot, but still, this has some potential. And one can also try to optimize for low costs in various ways. I think that this technology is still very much at the fundamental research stage. So it's not clear when and how these robots will be used in the future. But I think there is some potential for robots that are resilient, adaptive, and autonomous. So maybe some kind of environmental monitoring tasks to like designing robots that are very energy efficient, that can walk in different terrains or otherwise move around and be autonomous for a long time. For example, in a type of swarm systems or types of soft robots. So maybe one can imagine something like environmental action robots that go and monitor environmental waste and do cleanup. Yeah, so then I think I will summarize. And I've talked about bio-inspired and evolutionary robotics, where we take inspiration from natural evolution, and also we do take principles from nature, such as decentralized modular controllers and various ways of generating robot bodies to shortcut the design process to have robust designs. And how we use these algorithms to explore adaptation to environments and to different tasks, and see how the body and control both change as we let them do different tasks. And we can see some trade-offs, and it can be used as a design help. Especially these quality diversity algorithms are very interesting when it comes to exploring different designs and having different solutions to problems. I also talked a bit about how we can compare evolution from simulation and evolution only in reality, and what the different challenges are with this. Yes, I think I have one last video, but I will skip it in the sake of keeping the time, and I will move to the thank you slide, where I thank also all our collaborators, especially the PhD students and postdocs who have been doing most of the hard work in this case. So thank you.
No, thank you so much, Kyrre, for the presentation. So now we would really like to hear from the audience. So if you have any questions, type them in the AFO Neural Network chat room. And we have received already a few questions. So I would like to ask a question, first of all, on the reinforcement learning that you have been explaining throughout your presentation. So how is this reinforcement learning driven by human feedback, or is the robot learning by itself? How does it work?
So yeah, so I mentioned reinforcement learning as a way of training the robot controller, although not going too much into detail about that. But usually this is a process that is automatic in terms of one defines a performance measure for the robot, such as being able to walk fast forwards, or being stable while also moving fast, for example. And then you define this as something called a reward function that can be described mathematically from what you observe on how the robot is behaving. And this will then be fed back into the algorithm to have an automated process, an iterative process that adjusts a solution such that it gradually improves.
Okay. So we will now move to the next question. So Reshma, she's asking, what's the role of simulation versus real-world experimentation? How well do evolved controllers in simulation transfer to real-life users? Reality gap.
Yeah, so thank you for the question. It's quite interesting, and it's a problem that has been occupying this research community for a long time. So in some cases, depending on the simulations and how exploitative these algorithms are, the mismatch between simulation and reality can be quite big, and you can like see that the robot maybe doesn't move at all in the real world, or maybe it moves backwards or does something completely different, or it could be like more subtle that it deviates from its course, and that of course is not so good. So you can't really trust what you get in the simulation. And there's a couple of methods that have been proposed to address this. And maybe the most common way now is to introduce noise in your simulations. So you simulate multiple times with different amounts of noise in your sensors, in your actuators, and also in the size of the parts of the robot, such that the control systems that are learned will be quite robust to these kind of changes. And then when you transfer to the real world, it's more likely that the robot will also behave more robustly and behave as intended in the real world.
Okay, so I think we have another question now from on basically like if you could describe a near future scenario in many different areas like healthcare, agriculture, disaster response, where biologically inspired adaptive robot clearly outperforms conventional robots, and what unique capabilities would this bring to the table, and why would a traditional design fall short?
Yeah, that's a very good question. And this is, of course, like we're always in look for this kind of killer application. So right now we're more in it for like what we perceive as an interesting approach, and like we feel that there is a lot of potential, but we haven't really identified maybe the killer applications. But in my opinion, I think, for example, if there's robots that need to be very like produced in large numbers, for example, such that it's very important to have a low cost on each of them. These types of algorithms could be useful in trying to find power efficient, low cost designs. And well, another example, like for this bullet train, where you need to somehow optimize to have more energy efficiency, or say more more aerodynamic properties. These algorithms are already in use quite a bit, I think, in industry today as plugins into engineering tools and so on, so that you can optimize various parts of your design. So this is not really so much about autonomous and adaptive robots, but more about like being used in engineering in general. Also, like say for car design or such things. Yeah, I think probably like autonomy is a key keyword, and long-term autonomy and mass production, where you could really benefit from these types of optimizations.
Yeah. Yeah, and a follow-up question is, do you see biologically inspired robotics becoming the dominant approach in the, I don't know, in the next 5-10 years, like really leading to shape-shifting machines, self-repairing robots, or like how do you see, like more as a broader question, the future of this field, and if it's gonna really dominate the robotics scene in the next 5-10 years when it comes to all these diverse applications?
Yeah, that's also a good question. So I think currently the mainstream of AI for robotics research is not so much considering this, but there is some interest, and there is a growing interest in this co-design of the robot shape and the control. And I think maybe, for example, like this soft robotics field is also a quite growing and interesting field these days. And this calls for this type of algorithms to design and to optimize. So So I think as like more unconventional materials and actuators are easier to produce, also these algorithms are more interesting to use. So there are some materials, for example, that can change shape by applying different voltages. And this could enable shape change without having too much cost in terms of like additional motors and so on. And that would make it more attractive to use also in more types of robots and mechanisms.
Okay. Yeah, because I mean, you have been talking about co-designing morphology and control using these evolutionary algorithms, but like really, how do you see this approach scaling from, like real world deployment beyond the lab?
Yes. No, I think we're still quite far from going out of the lab in a way, but we're like seeing. I think it depends. Depends a bit on the mechanics, the materials, the actuators. Like so, as this is growing more mature, we can also start to apply these methods, and it has potential for various autonomy tasks. Yeah.
Okay.
Yeah.
And I mean, you mentioned as well that one of the big challenges was the reality gap. And like, what are the strategies that you are like using for bridging this gap? And I mean, there is domain randomization and others. Like, how are you trying to overcome this limitation?
Yes. So there is the domain randomization, so adding this noise into the algorithms that we talked about a bit. And then there are other approaches. Like we experimented a little bit with having this continued learning or adaptation on the real robot after having been transferred. So like the logic behind that is that like likely the robot has found say reasonable way of locomote in the simulation, but there might be small things like friction or motor strength that kind of puts it off a little bit and disturbs this kind of good interplay between the body and the control. And by adjusting a little bit, one can kind of find back some of this. And there are also some other methods that have been studied. So that there's like a ways of sampling in the real world, like doing most of the part in simulation, but sampling a bit in the real world to build a model of what kind of robot designs and what kind of controllers transfer better than others. So you can kind of avoid those areas of the search space that are not so transferable according to your model. And that could be like a hybrid way to kind of get data from the real world and try to steer in the right direction, so to speak.
Yeah. And can you combine these two methods the same time, or like is either one or the other? How?
Yeah, I think it should be definitely possible to combine these methods. It becomes more complex as a research experiment, but I think in a real system, you could probably do these kinds of combinations and do all of them basically. Yeah.
Okay.
Yeah.
So I think we are reaching out well, like time is almost over. So I don't know, like Kyrre, if you would like to add any other comments on the future of this field for our audience.
Yes, so I think it's a very, very interesting and fun field to do research in. So I encourage you who are interested, thinks this looks fun, to check out maybe some of the tools and the algorithms and see if you can participate and join us in this research in the future. That would be great.
No, and I'm sure, like Kyrre, this discussion is gonna definitely continue at the upcoming AI for Global Summit in Geneva in July, where we're gonna be exploring how to use these technologies to solve some of the humanity's biggest challenges. So stay tuned for the early program that has already been released, but more sessions are being added that are gonna be looking into this intersection between, like soft robotics, bio-inspired robotics, and more. So yeah, looking forward to discussing more in July. And I would like to thank you for joining us for today's AI for Good Discovery series event, and to all the attendees for making it such an interactive discussion with great questions. And we look forward to welcoming you at the summit and in future AI for Good robotic sessions. We encourage you to check out the AI for Good program online to see more robotic sessions that might be of interest to you. And now this is the end of this AI for Good event, and I would like to give the floor to Anna for the closing information. Thank you very much.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.